Hi, this is John Whitaker for the Mathematical Analysis 1 class, and this is our 33rd video lecture. And today we're going to start off by classifying types of discontinuities for functions. So I'm going to write up a definition that incorporates those two types that we want to look at. So here's definitions. We're going to let f be defined on a to b, so this is a real value function here. If f is discontinuous at a point x, and if the right-handed limit and the left-handed limit exist, then f is said to have a discontinuity of the first order. Or a simple discontinuity. And a second order discontinuity is the other type of discontinuity, where at least one of those left or right-handed limits does not exist. Otherwise, this discontinuity is said to be of the second order. We want to next look at some examples. The first example we look at is we'll define f of x to be equal to minus 1 if we have x is an element of minus 2 to 0, and 1 if x is an element from 0 to 2. Okay, so here's the way that this is defined, and I'm sorry, I want it to be defined at 1. I'm sorry, at 0, so I can have this closed. So here's the way that I have it defined. From 0 to 2, it's 1, so open circle here. Here's 2, open, 1, and then it's equal to minus 1. Here's minus 1, and it's closed here. Here's minus 2, open to there. And this f of x has a first order discontinuity at x equal to 0. It's because the left-handed limit is equal to minus 1. That means the left-handed limit exists. And the right-hand limit at 0 is equal to 1. And so that means that the right-hand limit exists, but it's discontinuous. Okay? That's what we call first order. here, the second example, we'll let f of x be equal to x minus 1 if x is an element from -3 to 3 and x is different than 1, and we'll have it defined to be 2 if x equals to 1. And so we'll go to graph this. Here's what it looks like. So 1's here, and it's x minus 1, so at 0 we get out to -1. At 1 we would get out 0, which is missing, and so here's what it looks like, and it's to 3, so -3. At -3 we're at -4. And at 3 we're 2. And then we're 2 here. Okay, so that's what it looks like. I'm sorry. Yeah, that's what I want to find. Okay. Then f of x has a first order discontinuity at x equal to 1. We'll look at another example. So we define f of x equaling x if x is rational and it's equal to 0 if x is irrational. Okay. Then here's what I want to tell you. First of all, as a kind of a nice observation, f of x is continuous. At 0. But f of x has a second order discontinuity at every other point. All right, now I want to go through a series of definitions, and then we'll do a little bit more examples. We let f be a real valued function on A to B. Then f is said to be monotonically increasing. Monotonically increasing is what I write here. You know, before I finish this definition, I want to stop for a second. Look, you know why we have a second order discontinuity at every other point? It's because if you take either a rational or irrational point, you can get to it at every, you can get to it through a sequence of points that are rational or irrational, and that sequence, the sequence that either consists of all rational or irrational points, that's all it's in the sequence, will either be going to 0 or the point we're going towards. Okay? And so that's what's going to make this second order. That means that let's say the right hand limit won't exist. I'm going to say that again. Okay? So if you take like a rational number, let's say 1, then I can get to 1 through sequences. Bigger ones. I'm coming in from the right. Okay, I can come in through sequences that are all rationals. Okay, and what that will go toward is 1. Okay, yeah. But if I come in from the right with a sequence that is all made up of irrational numbers, okay, then f of that sequence is going to be 0, and so we don't get that limit exists. Because we get 2 different numbers. Okay. All right, anyway, we're in the midst of this definition. We let f be a real value function on a to b, then f is said to be monotonically, I'm going to find increasing. Monotonically increasing on a to b. If when you have a is less than x is less than y is less than b, that implies that f of x is less than or equal to f of y. Another definition, we got monotonically increasing. We have monotonically decreasing. So we let f be a real value function on a to b, then f is said to be monotonically decreasing on a to b if a being less than x being less than y being less than b implies that f of x is going to be greater than or equal to f of y. Okay, here's another definition. And this is an all-encompassing definition, 2 previous definitions. It says, let f be a real value function on a to b then f is said to be monotonic that's monotone, okay, to be monotonic or be a monotonic function if f is either monotonically increasing or monotonically decreasing. And as an example, first of all, several examples, we have f of x equal to x. That is monotone, it's monotonically increasing. And here's what's happening. It is this diagonal looking function, and if you take any x value bigger than y, what happens is the output values for x, it's going to be less than the output value for y. As you read from left to right, the graph's going up. Well, the graph's not going down, let's say that. That's what it means to be monotonically increasing. Could be staying the same. It's at less than or equal to. F of x is less than or equal to 1. Okay. Another example is that f of x is equal to minus x plus 3 minus 2x if x is less than 0, and here it's if x is greater than or equal to 0, is monotonically decreasing. When you look at its picture, here's what it is. So if you're to the left, let's see, if I stick in minus 1, I get out 4. Okay. The 0 here looks like this, and then minus 2x if we're so stick in 0, you get out 0. If I stick in 1, I get out minus 2. This. Okay, and you see that it's always going down as you read from left to right. Then a third example. Is that of cosine of x. Let's look at it. Okay, so what does it look like? It looks like this. If you stick in 0, you get out 1. Stick in pi over 2, you get out 0. Pi minus 1. 3 pi over 2, you get out 0. 2 pi, you get out 1. Of course, it continues this pattern. And so it looks something like this. And this, then f of x is not monotonic. And the reason is, if I take 0 to the power 2, it's definitely f of 0 is definitely bigger than or equal to f of pi over 2, so it might be decreasing, but later we see, if we compare pi over 2 to 2 pi, the f of pi over 2 is less than or equal to f of 2 pi, so can't be increased, can't be monotonically decreasing, and therefore it's not either of them. Okay, well, let's get to the only theorem I think we'll prove during this session. Here's what it says. It says, let f be monotonically increasing on A to B. Then f of x plus and f of x minus, so the right-hand limit and the left-hand limit, they exist for, or at every point x in a to b. Okay. Okay. And here's what we have. So this is still part of the theorem. More precisely, what we can say is that the soup over all t values, where t is sandwiched between a and x, what that's going to be equal to is the left-hand limit of x, which will be less than or equal to f of x, which is less than or equal to f of x, the right-hand limit, which equals to the thing over all t's bigger than x, but in the interval, f of t. Okay. Furthermore, still part of the statement of the theorem, if a is less than x is less than y is less than b, then f of x plus is going to be less than or equal to f of y minus. So that's for this monotone increasing sequence. We could have an analogous statement for a monotone decreasing. Okay. All right. The proof is going to be really having three parts, if you will. The first two parts are going to be very similar, and then this last part is short. Okay. So here's the proof. We let f be monotonically increasing on a to b. Okay. We let x be an element of a to b. Now, since f is monotonically increasing, then for every t element from a to x, f of t is going to be less than or equal to f of x. So if you look at f of a to x, so this image, the output values, okay, this is bounded above by f of x. Okay? Right. And this is a non-empty subset of real numbers, and it's bounded above, and the real numbers have the least upper bound property. That means that the supremum of f of a to x exists call it A. So A is what I'm letting represent the supremum. Okay. By definition of A, then A is less than or equal to f of x. Hey, look, f of x was was the upper bound of this guy, and this is the least upper bound. So A has to be less than or equal to f of x. We want to show
that A is equal to the left-handed limit of f at x. So the way we do that is we're going to show that if you give me any sequence, so I'm going to give you a sequence, t sub n, that's in a to x, okay, and we've got to have some, that sequence converges to x. And t sub n converges to x. We want to show, so we let this happen. We want to show that f of t sub n equals to x, because f of t then, that's going to be equal to that. The left-hand limit here. All right. So we let epsilon be greater than 0 be given. We need, I should say, and n element of the natural numbers such that for all n greater than or equal to this big N, the absolute value of f of t sub n minus a will be less than epsilon. That's what it means for that sequence to go to A. Well, here's the first thing you should note. Note a minus epsilon is not an upper bound for f of a to x. Okay. That's because a is the soup, so you go a little bit lower than that. That's not an upper bound. Well, what that means is that there exists an x sub 1 element of a to x such that a minus epsilon is less than f of x sub 1. And we know that f of x sub 1 is going to be less than or equal to a. Okay. Now, since t sub n's converge to x, that means there exists an n element of j such that the distance between t sub n and x will be less than, and the epsilon here I will work with for this convergence is going to be x minus x sub 1. So these are not the same here, so their distance is a positive number. X and x sub 1 is not the same. The reason x and x sub 1 are not the same is that x sub 1 comes from the open interval from a to x, so it can't be equal to x. Okay. So this is true for all n element, or for all n greater than or equal to this big N that we have. Okay? So that concludes that sentence. So rewriting that, what we have is, let's see, the x's are always bigger than the t sub n's. So that means that x minus t sub n is going to be less than, and here the x is bigger than x sub 1, so it's x minus x sub 1. And that's for all n bigger than or equal to big N. So what that says is minus t sub n is going to be less than minus x of 1, and that's true for all n bigger than or equal to big N. Okay. So just using algebra here, that says that multiplying everything by minus 1, that says that t sub n is going to be greater than x sub 1. And that's true for all n bigger than this big N. Okay, well, since f of x is monotonically increasing, then what we have is that f of x of 1 is going to be less than f of, less than or equal to, f of t sub n. And that's true for all n bigger than or equal to this big N. All right. So that says for all n bigger than or equal to this big N, what we have, well, we have that a minus epsilon is going to be less than f of x sub 1, which is less than or equal to f of t sub n, which is less than, well, it's less than or equal to a, so it makes it less than a plus epsilon. So, for all n bigger than or equal to n, here we have, concentrating on what we want to concentrate on, a minus epsilon is less than f of t sub n, which is less than a plus epsilon. So rewriting that by solving, by adding epsilon to both sides. I'm sorry, by subtracting a from both sides, that's what I should say. Here's what we have. This is the statement for all n bigger than or equal to this big N. We have minus epsilon is less than f of tn minus a, which is less than epsilon. So this says for all n bigger than or equal to big N, that says the absolute value of tn minus a is less than epsilon. So that says f of tn converges to a, and that's what we wanted to show. So as a conclusionary statement from this part, that says f of x, it would be minus here, is equal to a. That's what we need to show. All right, so now we kind of repeat this same process, except we're going to work with the x plus, and so instead of infimums, instead of supremums, we're going to work with infimums. So similarly, since f is monotonically increasing, every t element of x to b, then we're going to have f of x is less than or equal to f of t. So what that tells us is the set f of x to b is bounded below since it's a subset of the real numbers, it's bounded below, then the infimum exists. m of f of a to b, exists, say, b equals to the minimum of this set. I'm putting these little squiggly lines around just to kind of see what we're talking about. Okay. All right. By definition, of b being infinity, and this was wrong. It's not from a to b. It's from x to b. Okay. Okay. By definition of b being equal to infinity, what we have is that f of x is less than or equal to b. Okay? That's because f of x is a lower bound. Okay? B is the greatest lower bound. What we want to do is we want to show that f of x plus equals to b. So how do we do this? Well, you give me any sequence that's coming in from the right of x, I will. Let's call it t sub n again. This is a different sequence than we had before, even though I'm using the same symbols. So let it be a sequence n here, x to b, okay, with t sub n converging to x. We want to show that f of t sub n converges to b. That's what we want to show. All right. Well, we let epsilon be greater than 0 be given. Just a second. Just want to look at something. Okay. We let this be given. What do we need? We need an n element of the natural numbers such that for all n greater than or equal to n, that's the value of f of t sub n minus b is less than epsilon. Okay. All right, well, note, since b equals to the infinity of f of a to b, then b plus epsilon is not a lower bound. F of a to b. It's not a to b, it's x to b. Gosh, have I been writing a to b? I've been saying x to b. That's what it should be. Okay. Sorry. Okay, so that's not a lower bound. Thus, there exists an x of 2 element of x to b such that f of x of 2 is less than b plus epsilon. Now, since t sub n converge to x, there exists an n element of the natural numbers such that for all n bigger than or equal to big N, what we have is that the distance between t sub n and x will be less than, well, I'm going to have it be less than x and x sub 2. And again, x sub 2 is in this interval, so it can't be equal to x, so that's not 0. This part is non-zero. So, for all n bigger than or equal to n, let's see, here, the thing that's always bigger, the t sub n's are always bigger. So this is t sub n minus x. And here, the thing that's always bigger is x sub 2, so this is less than x sub 2 minus x. And so, having said that, we could say something for all n bigger than big N. Okay, what we have is that t sub n will be less than x sub 2. Okay. All right. So since f is monotonically increasing, then for every n bigger than or equal to big N, we have that f of t sub n is going to be less than or equal to f of x sub 2. And of course, this is less than b plus epsilon. So for all n bigger than or equal to this, for all n bigger than or equal to this big N, remember this guy has got to be bigger than or equal to b, so we have b minus epsilon is less than f of t sub n, which is less than b plus epsilon. So, for all n bigger than or equal to big N, here's what we have. We have minus epsilon is less than f of t sub n with minus b, which is less than epsilon. So for all n bigger than or equal to big N, we have that absolute value of f of t sub n minus b is less than epsilon. So what that tells me is that f of t sub n is equal to b. So f sub t sub n converges to b. Thus, by definition, that says that f of x, the right-hand limit is going to equal to b. So what we've come up with for the first two parts is we have shown that the sup a less than t less than x of f of t equals to f of x minus, so this guy is this, which is less than or equal to f of x, which is less than or equal to f of x plus, which equals to the infimum over x's over all t's that are bigger than x but yet less than b. Okay. All right. So there's only one little part left of the proof, and here's what that is. So the final statement. So we let the final statement of the theorem is what we need to prove. Let a be less than x, be less than y, be less than b. We want to show f of x plus, so the right-hand limit, is going to be less than or equal to left-hand limit at y. Okay, now, here's the first thing we observe on this part of the proof. So note, since F is monotonically increasing, F of x plus, which equals to the infimum of all the f of t's over t's, so plus, this is bigger than x, it's less than b, is equal to the infimum of all the y's, of all the t's that are bigger than, so all the t's, over all the t's that are bigger than y, but yet less than b, of f of t. This has to do with the increasing nature. I didn't write down what I wanted. Here, this is wrong. It's x and here's y. Okay. Look, here we're looking at the interval from x to b, okay? And we look at the infimum over that. And that's going to be the same thing as the infimum over this, where y is less than b, because we know that we are increasing function. So essentially, the picture is this, okay? Something like this. Here's x for a second. I don't care what's happening here. But here is b, and here is y. And so if you want to find the infimum over the output values, okay, over this part, okay, whatever it is, it's going to be the same as the infimum over this part because it's an increasing function. Similarly, f, the left-hand limit at y, which equals to the sup over all t values in between a and y of f of t, is equal to the sup of all the t values in between a and x of f of t. I made a mistake again. So here, this should have been x, and this should be y. And that's, again, because f is monotonically increasing. And it's the same type of picture. You know, here's A. Let's say it like that. Then, if you want to find the sup over this part, okay, that's the same thing as the sup over this part. Okay, we're almost done. Since the nth of f of t, x being less than t being less than y, is less than or equal to sup at x less than t less than y of f of t, then f of x plus is less than or equal to f of y minus. And that's the proof. Ladies and gentlemen, that's it for this video lecture. Thank you very much for your time and patience. One more video lecture to go for the class.